we're going to take a look at how sample data, or knowing that we have sample data, changes some of the things that we've learned to do so far in statistics. So sample statistics, the sample, again, is used to represent the population. But this is an important thing when we realize that we have especially a small sample. The formula for the standard deviation is going to change a little bit. Okay, not that much. Our other sample statistics are going to be the same as if they were the population. So, for example, to get a sample mean, you're going to add up all the data and divide by the number of data you have. And right here are the two formulas that we have used to do that. Notice instead of using mu, which would be the population mean, we're using x bar to mean the sample. As we move into testing, we're going to need to understand what degrees of freedom are. Now, degrees of freedom mean basically that as you have data, the last data has to be a certain number in order for you to get a certain mean. So, for example, let's say that I have test scores of 56, 76, 80, then I don't know what this one is, and I know that I have an average of, say, an 83. And this, I'm just using this as an example to explain what degrees of freedom are. These three scores right here can be anything, okay? And I still could possibly get this mean of 83. But after I have this score, this score, and this score is forced into a value. It has to be something after these other three. So we would say in this situation that there are 3 degrees of freedom. And in general, we have, if we have a certain number of data, our degrees of freedom, which I think is up there anyway, but our degrees of freedom is 1 less than our sample size. That's the idea there for degrees of freedom. So if I have a sample size of 30, then my degrees of freedom is 29, 1 less than the sample size. And that's saying that 29 of those data points could be anything, and then the 30th one has to be a specific number in order for us to get a certain value for our mean. Okay, so sample variance and sample standard deviation are going to have slightly different formulas than if we were dealing with the population. We have to correct for an error that pops up, and that being that our deviation, like if we were to know what the population standard deviation is, our sample standard deviations tend to be just a little bit off. And there's a correction for that, and that's to decrease in our formula, to decrease our n, our sample size, by 1. So why that works out is not a discussion for now. It's just like, know that we need to do that. So that does change our formula a little bit. So when we're talking about a probability, like if we have a probability distribution, if we have, say, a sample size of 12, then we know that to find our probability, it would be some number over 12. But in this case, we would do that some number over 11 because we have 11 degrees of freedom. That's where that n minus 1 comes in. And I know that looking at the formula is kind of like confusing, but when we go over an example, it'll make sense. So standard deviation still is the square root of the variance, and there are the formulas right there. And we need to reflect our degrees of freedom. So suppose we have these 5 scores right here. They're measuring plant growth, and this is what they got. And we know that this is a sample. This isn't all the plants. This is a small sample of the plants. It's 5 plants. So note that our degrees of freedom is 4. We have 4 degrees of freedom, and then that fifth number has to be a certain value in order for us to get a certain mean. So we want to find from this the sample mean and the standard deviation. I know that you know how to find the mean, but I'm going to go ahead and go through it. So x bar is going to equal 13 plus 15 plus 18 plus 10 plus 14, all divided by 5. So we really don't need to change anything when we know that we're working with sample statistics to find the sample mean. It works the same as if it were the population. And so in this case, I get x bar is 14. Okay, now this is where it's going to get a little bit different. Let's calculate our variance. So our variance is going to equal 13 minus 14 squared plus 15 minus 14 squared plus 18 minus 14 squared plus 10 minus 14 squared plus 14 minus 14 squared. And then instead of dividing by 5, which is the number of data I'm going to have, I'm going to divide by 4. That would be 5 minus 1. And that's going to give me my variance for the sample. So it's a slightly different formula than what we are used to. So I'm just going to take a second to type that in. And let's see here, 4 squared, doing all those subtractions. 4 squared again. Hopefully I don't make a mistake in this. And I get a variance of 8.5. Which means my standard deviation, which is going to be S, is going to be the square root of 8.5. Which I'll do here in a second. And I get equals 2.915. Okay. So all this to say, just slightly different than if it was standard a population. Okay, so Ozzy wants to know the number of Skittles in the package. He took a sample of 4 packages. So obviously he's not counting all the numbers of Skittles in all packages of Skittles. So he took a small sample of 4, which means in this case, my degrees of freedom is 3. Okay, 1 less than the sample size. So to find our mean, we would do 50 plus 48 plus 53 plus 46. And so really, for our purposes, the fact that we're using a sample doesn't really come in until we're calculating variance or standard deviation. Then it's going to matter, and only matter ever so slightly. So when we type this in, we do get a, hold on, typing it in right now. We do get a mean of 49.25. Okay, now when we go to do our variance, we are going to do 50 minus 49.25 squared plus 48 minus 49.25 squared plus 53 minus 49.25 squared. And so you really should be thinking, gosh, this is something that we've done since the beginning of the year, and that is certainly true. The only difference being, in this case, I'm not going to divide by 4 for my variance. I'm going to divide by 3 because I have 3 degrees of freedom. So my variance is going to be, actually, I'll put that up in a second. My standard deviation is going to be the square root of my variance. So in this case, it is 2.9861. And that means I was actually cheating on my calculator having it do it all. So the variance was about 8.9168 about, because basically what I did is I put this in my calculator and worked for my standard deviation back rather than type all this in, waste time. Okay, so now another example of this, if we have like a table, a frequency table. No, we could do it with probability. Like suppose it was a probability distribution. Now, you don't need to do this step. Like you could type all of this in the calculator and use list 1 as your X data, list 2 as your frequency, and your calculator will pop out your standard deviation, your mean, and you'll be looking for that S. But what if this were a probability distribution? What am I going to do here for my probabilities? So I see that I have 3 plus 5 plus 4 plus 6, so I do have 18 data. But when I go to do my probabilities, I'm actually going to use 17 because I only have 17 degrees of freedom, which does mean when I go to add up these probabilities, I won't get 1. I won't get 100%. I'll get something a little bit over 100%. And when we're working with sample data, that is okay. So this is our sample. And when we go to find our X, and let's just go ahead and put this in. Got to type it into the calculator, but we would actually do 8 times 3 over 17 plus, now this is for, I'm going to use this if, so sorry, this will be 18. Use with standard deviation and variance. For the average, we actually will do like 3 over 18, 5 over 18, 4 over 18, 6 over 18. It works the same as if it were a population for the mean. It's for variance and standard deviation where it's different, and you'll have to use a 17 over here for your probability instead. So I'm still typing this in. And what we get here, so I'm going to add this up, write down what I'm doing. So 5 over 18 plus 10 times 4 over 18, and then finally 11 times 6 over 18. And that's a way to get your mean. You multiply each data by the probability that it happens and add it all up. And we do get 9.72 approximately for our mean. Our variance, okay, now our variance is going to be 8 minus 9.72 squared. Now we're going to use this instead of the 18. Plus, now we'll have 9 minus 9.72 squared times 5 over 17. So notice the probability I've just decreased by 1 for the variance, and we'll do the same thing for the standard deviation because I only have 17 degrees of freedom. So what's different? Well, everything works the same except that variance and standard deviation. So you just got to remember to change it. Now your calculator will do this for you. And what you will be looking for, again, is instead of looking at sigma, which would be the population standard deviation, you'll be looking at S, which is the sample standard deviation. That's what you'll be looking for, if you know that you are indeed working with a sample. Okay, so that gives us our variance, and then our standard deviation is going to be the square root of our variance, and in the end, in this case, we should get about 1.127, okay? I think that wraps up this section, but what we'll move into is now how do we do hypothesis testing when we have a small sample size.